Hey guys, happy late Arbor Day. Um, so I'm going to be doing a video here for you guys about finding the Earth's volume. Uh, so without any further ado, let's get started. All right. So I'm sure you guys kind of knew. Um, First thing that comes up is using the 1/3 part. You know, and I know at first it may not look as impressive. You're like, oh, okay, yeah, we already know what the formula is. But um, do we really? So we're going to be using an iterated integral over a region. Um, and then we're going to have r cubed here. And then this is going to be in respect to dA. And I can already tell most of you guys that this is quite not what you're used to as far as uh, finding the volume for something. So big is it, Anyways, so moving along here. So we're going to have to define this region. And the region is it's going to be on 0 here on both on the x and y axis. But it's also going to be going from 0 to 4 over here. And you can swap the 4 and pi here. You can swap them for the x and y. That part really doesn't matter. So long as whenever you're going through the integral, you keep these the same. Especially for these parts right here, when you're doing similar integrals. So right here, what we're going to do is we're going to start off rewriting this formula or equation, if you will. So we're going to do this. It's going to be from 0, 0, and we'll have dx on the inside. So we're going to have pi right here and 4 right here. It may be kind of hard to see, but you have it's pi and 4 right here. And then we're going to have r cubed and then dx dy. So we're going to solve our first one right here, which is from 0 to pi r cubed dx. So it's going to look something like r cubed x from 0 to pi. And then when we rewrite this out, we're going to have r cubed times pi plus c minus r cubed times 0 plus c. And that's what we have right here. So the plus c's cancel each other out. Anything times 0 is 0. So everything over here on this side right here is just 0. So all we're left with is r cubed times pi. So r cubed times pi. And then this right here goes in as for our next integral, which is, it's the iterated integral. So from 0 to 4, right? Which is this one here. And then we're going to have r cubed times pi dy. So then it goes r cubed pi y from 0 to 4. And we're obviously just repeating the same steps. And you're just using the fundamental theorem of calculus right here. So as we continue, we have r cubed times pi times 4. And here plus c minus r cubed times pi times 0 plus c. And just like what happened from over here, the c's cancel each other out. Anything times 0 is 0, so everything over here is 0. And then all we're left with over here is r cubed times pi times 4. And if it looks like we're done, sadly mistaken. Because as it turns out, we still have this 1/3 in the front, right? So when we come back over here and we take a look at it, we still have the 1/3 times r cubed pi times 4, right? And if we rewrite this, because we always, it's always nice to make things rewritten as a, well, you know what I'm trying to say. Anyway, so we have pi off. Jeez. Anyway, so we're gonna rewrite this as with the 4 in the front, so 4 pi r cubed over 3. And if that looks familiar, it's obviously because we have the 4/3 pi r cubed, and that's how we got that from this whole integral. So we found the volume of the sphere, but if there's one thing that we do know, it's that the Earth's not a perfect sphere. So how do we compensate for that? I'll show you in a second. Okay, so we found the volume of the sphere, but now we need to figure out how to find the volume of an ellipsoid, which more closely describes the Earth. So, just to write down a few little facts here, I'm going to say, well, actually, no. So we're going to make a few modifications to this one right here, and you can still use the very same math, right? But for the integral, instead of having r cubed, we're gonna replace that. So we're gonna go from this, and we're gonna say we need 1/3. Oh geez. For this integral here, and then we're gonna have a times b times 2 times a plus b over 3 dA. And so this is the path that you would take to figure out the volume of the Earth. Now you might be thinking to yourself, okay, well, what's A and what's B? Well, luckily I've got a paper here that'll I've already got this for you guys. So A, right? So A equals 63 or 6,378.1370, and B equals 6,356.7523. And so those are the two numbers that you plug in for A and B, where you have AB times 2 times A plus B over 3. And to give yourselves like a really quick visualization of what we're looking at here. So remember, the Earth isn't exactly that perfect circle or that perfect sphere, right? But we do know that from the center right here, we have this one. We should have this one, and then there's that one. So it looks something like that. So here we have like A, B, and this one right here is that 2A plus B over 3. So you kind of get like the whole 3 different, like you have like one here, one's going this way, and then it kind of looks something like that. And you're getting those 3 different distances from the center. um, which helps in the accuracy. And each of those you would see that like of like on a in a regular formula for an ellipsoid would be it'd be R1 times R2 times R3, which is essentially what we're getting, where R3 is 2 times A plus B over 3. Um, so, and to touch up on that, I'm not like too familiar on why that is the way it is. I'm sure we could all do some personal research on our own if we wanted to figure that out. But so yeah, um, well, that's all I got for you guys. So see you next time. Happy Arbor Day.